Class, in this video, we're going to talk about correlation, variance, and covariance. Correlation is a concept that we learned in intro stat course. I am not going to get into too much details about it. In case you need a little bit more help, you can watch the video, a link I provided here. This is just a quick reminder. We use correlation to measure a linear relationship between two continuous variables. And the formula, conceptual formula, is given here. This is just to show you when you calculate correlation, you actually have to standardize the two variables first. So after the standardization, both variables have a mean of 0 and the standard deviation of 1. The possible correlation value is somewhere between -1 and +1. The closer it is to 0, the weaker the relationship between the two variables. The sign of the correlation value only tells you the direction of the relationship. It could be a negative relationship or positive relationship. It's the absolute value of the correlation value that shows you the strength of the relationship. The closer the correlation is to either -1 or +1, the stronger the relationship between the two continuous variables. When there is a correlation between two variables, you actually can take a step further to do regression. One variable will serve as the independent variable. The other variable will be your dependent variable. And because regression is built upon correlation, the regression coefficient is related to the correlation between your dependent and independent variables. And here's the formula that shows as long as you know the correlation between the two variables and their standard deviations, you can calculate the regression coefficient. One thing, let's make it clear, is that correlations are comparable because they are based on standardized values. I gave you some examples here. Let's take a look here. If we have two variables, x1 and y1, they have a correlation that is -0.5. Another two variables, that is x2 and y2, they have a correlation of 0.2. You actually can tell the correlation between x1 and y1 is stronger than the correlation between x2 and y2, even when you don't know anything else about those variables. All right, let's talk about variance and covariance now. Variance, if you remember, is a way to measure the variation of a variable. If you know the variance of a variable, you take a square root of the variance, you get the standard deviation of that variable. Covariance, on the other hand, it's like an unstandardized version of correlation. It measures the association between two continuous variables. Let's call them x and y here. I gave you two sets of formulas here. One set is to calculate the variance of a population and the covariance of a population. The second set is for the variance and covariance of a sample. By doing this, I want to give you a quick reminder that for every statistic that we're interested in, it could be the mean, could be the standard deviation, there are two values. One is the real value from the population. We call it the population parameter. Most likely, more than 99% of the chance we do not have access to the population. So we have to use a sample to estimate the population parameter of a statistic. So we call that sample statistic. So we use sample to calculate the variance and calculate the covariance. You can see that the difference is whether we know the population mean or we only know the sample mean. The second difference is that this is the population size. This is the sample size minus 1. Here is actually called the degrees of freedom. In this course, since we assume we do not have access to the population data, we do our research with sample data that's a little fraction of the population. We are going to concentrate on the population statistics. Okay. So the next question will be, what is the difference or similarity between correlation and covariance? Well, both of them are used to measure the strength of association between two continuous variables. The difference is that for correlation, you use standardized variables. So the correlation is limited to a range from -1 to +1. However, for covariance, the two variables are not standardized. The value of covariance is dependent on the metrics or the values of the two variables, x and y. Let's see, the variable x is salary. It measures on a dollar amount, has a value from 0 to $100,000. Okay, and variable x measures the years of employment. It could have a value from 1 to 50. The covariance between x and y could be huge because the salary amount can be very large. Okay. If we have another pair of variables, x is the high school GPA and y is the college GPA of a group of students. Even if the two GPAs have very strong correlation, their covariance would be very, very small in comparison to the covariance between salary and years of employment, simply because the values of salary can be very, very large. And the GPA values are limited from 0 to 4. Let me get to the point. Correlation values are comparable, but covariance values are not comparable. So why do we need to talk about correlation and covariances? Well, like I mentioned in a previous video, in SEM, we do not analyze the raw data directly. We analyze the correlation or covariance matrix that's generated from the sample data. In a separate video here, I showed you how to get the correlation or covariance matrices from a sample data in SPSS. Here, I just want to show you they are related, okay? This is our correlation matrix. Imagine in your data set you have three variables, x1, x2, and x3. So you put them here and put them here. This tells you this is the correlation between x1 and x2. This is the correlation between x1 and x3. This is the correlation between x2 and x3. Similarly, imagine you have x1, x2, and x3 here and here as well. You can tell this is the covariance between x1 and x2. Covariance between x1 and x3. covariance between x2 and x3. In both correlation and covariance matrices, we can ignore the upper right half here because they are simply redundant information. The values above the diagonal line are repetition of the values below the diagonal line. And you can find the value that's in this position symmetric to the diagonal line. So here is the correlation between x1 and x2. Here is the correlation between x1 and x2 as well. So when we write matrix, we only include the values that's on the diagonal line and those below it. All right, I spent so much time talking about correlation and covariance just to prepare for the last point. In SEM research, sometimes you see it's the correlation matrix that's being analyzed. Most of the time you see it's the covariance matrix that's being analyzed. I just want to help you to understand that you actually can convert back and forth between the two type matrices. In the covariance matrix, on the diagonal line, the numbers are the variances of the variables x1, x2, and x3. So this is variance of x1, this is variance of x2, this is variance of x3. That's why the complete name of this matrix is called the variance covariance matrix. In the correlation matrix, on the diagonal line, we have ones. Why? Because we know for standardized variable, they all have a standard deviation of 1. And the variance is a squared value of standard deviation. So when you square 1, you still get 1. So we have 1, 1, 1 on the diagonal for a correlation matrix. So to convert from a correlation matrix to a covariance matrix, what you need to do is identify what variables are involved for a given number, then multiply the standard deviation of the variable, okay? For example, if we talk about the correlation between x1 and x2, the two variables that are involved are x1 and x2. Their standard deviations are s1 and s2, okay? You time the correlation between x1 and x2 by the standard deviation of x1 and by the standard deviation of x2, you get the covariance between x1 and x2. Now imagine we have x2 and it has perfect correlation with itself. So x2 and x2 has a correlation 1. What are the variables involved? x2 and x2. So 1 times the standard deviation of x2 and times the standard deviation of x2 again, we have the standard deviation of x2 squared. That's how we get the variance of x2. If we know the covariance matrix, we want to find the correlation matrix. We do the stuff the other way around. For example, if we have the covariance between x1 and x3, we divide this value by the standard deviation of x1 and the standard deviation of x3, we will have the correlation between x1 and x3. That's how we convert back and forth between the two types matrices. The good news is that you do not have to do this manually. You can get both types of matrices from SPSS. You only need to understand how they are related to each other.